So we showed in the last section how multiple people could have a secure lottery on Bitcoin where each of them provides some randomness, and we combine that to get group randomness, and we use time hash commitments to make that process fair. In this section, we're going to talk about using Bitcoin to generate public randomness. So the same situation, we want to do a lottery, but now maybe we have so many participants that it's impossible to have everybody send randomness in. Maybe that's not the most convincing protocol to the public, or maybe it's just something that people aren't aware of yet. So what do I mean by a public randomness protocol? I'll go through a couple of examples to show how this is done in practice, because this is already used for a large number of applications. So one example that happens every spring is the NBA draft lottery. So all 30 teams in the NBA get together and they randomly choose, with some weighting based on how the teams did in the previous season, who's going to have the rights to draft the top amateur player in the country. So this was first done in 1985, and it was a little bit of controversy then because the New York Knicks won in the first year and they were able to select Patrick Ewing, who was a very highly touted prospect. And almost immediately after that happened, people alleged that there was a conspiracy and that this process was rigged so that the Knicks, who happened to play in New York, which is a large media market, were able to select the best player. So if you go online, you can find all manner of conspiracy theories for how the NBA rigged this process, such as the famous bent corner theory, which says that they pulled an envelope that had a bent corner out of the bowl of envelopes with different team names in them. And even today, they do this lottery every year, and there are a whole bunch of conspiracy theories that come out immediately every time they do it, alleging that the process wasn't fair, it wasn't truly a random draw. A more serious example comes from 1969, when there was a conscription lottery in the United States to determine which young men were going to be forced to join the armed services, most of whom were sent to Vietnam. So this was a somewhat similar protocol. Several congressional representatives carried this out. They dumped small capsules with every day of the year into a large plastic drum that you can see there. And then they took turns reaching their hand in to pull the numbers out. And participants in the draft were given a priority number, which determined how likely it was that they were going to be forced to join the military based on what day of the year their birthday fell on. So this is the first time that this was done in 1969 on a national scale. And the goal was to make this process more fair and to demonstrate that this was a random process. But unfortunately, they botched it. So the statisticians looked at the results of this within a week after the lottery happened, and they noticed a funny pattern that was, while it's somewhat subtle, it was very unlikely to have happened due to chance. And that was that most of the days late in the year received very low draft numbers. And the reason this happened when they went back and looked at the tape is that they turned the wheel over exactly an even number of times, so that the capsules that started on top tended to stay on top. There wasn't sufficient mixing. So while there was some mixing and it was somewhat random, it didn't turn out to be a truly random draw. So both of those examples show that it's very hard to do public randomness and convince the public that you've actually done a good job. There's both the risk that the public will not believe you and the risk that you'll actually screw it up in the process of trying to do this physical display of randomness. So for a long time, people have wondered, could we do better cryptographically? Could we have a service that we call a cryptographic beacon? And the idea is that this beacon, much like traditionally a beacon is like a lighthouse that sweeps out light at regular intervals, this cryptographic beacon will emit new random data at a regular rate. And the goal is that it will emit uniform randomness that nobody can predict in advance. So everybody agrees that there's no way to predict what values the beacon is going to output next. And yet every party can see the same values and agree on them. So if this perfect cryptographic beacon existed, the NBA draft lottery or the Vietnam conscription lottery, if you wanted to do a process like that, or even if you just wanted to play bingo at your local social club, you wouldn't need to use a large wheel or any physical display of randomness. If everybody trusted the beacon, you would save a lot of effort from having to have these small physical displays of randomness. There's a whole bunch of applications besides just lotteries. So various applications of auditing and voting systems, doing zero-knowledge proofs, cut-and-choose protocols throughout the security literature There are a lot of examples of things that can be done much more simply and efficiently if you had a perfect cryptographic beacon that satisfied all of these nice properties. So unfortunately, we haven't found a perfect solution for this yet. Like I said, the public display of randomness, so using a wheel, flipping coins, rolling dice, spinning a dreidel, what have you, that has been a solution that's been very popular throughout history because it's cheap and easy and everybody can see it and understand it. But this really doesn't scale to remote scenarios very well because it's very hard for people to audit, even if they just see a video, that you haven't been a magician. You haven't done some kind of sleight of hand where you swapped out the dice for weighted dice, or you somehow rigged the process. So it's very hard to establish trust remotely in any kind of physical process, which is basically the problem that the NBA has had for years, trying to convince fans that they're doing a fair process. And they've switched to a bunch of different technologies. They've done both the envelopes and ping pong balls bouncing around with fans. And people can always come up with some outlandish scenario where there's somehow cheating and there's more to it than you can see on the video. So for the purposes of this lecture, I think we can rule out a public display of randomness as something that we could ever have a high level of trust in. So the National Institute of Standards and Technology, NIST, has started in the last few years to run their own beacon. And the way they generate the random numbers is through a very complicated setup involving two entangled photons that gives you very strong guarantees that you have randomness generated from a quantum mechanical phenomenon. And if you believe the Heisenberg uncertainty principle and other basic core tenets of physics, then this should be random and nobody can predict it. And NIST has set this up as a machine, so every 60 seconds they publish a lot of random data and they sign it. So this is probably the most efficient thing to use. They just have a feed on the web. You can listen to their server, broadcast this stuff, and get all the randomness you want. And if you read their papers in the physics argument, there's a very strong argument that this is truly random and that there's no way anybody could predict it. Of course, you have to actually trust that NIST is doing this. You have to trust that somewhere in a building in Maryland they've actually built this, and they aren't just making it up, or that they don't have the ability at a specific time, if they want to overwrite the value with some other data that they happen to want. So this is sort of the limits, in a sense, of physical display of randomness, and it still hasn't gotten around this problem that you have one trusted party doing it, and unless you physically go there and observe the process yourself, it's very hard to have a high level of confidence that this was a fair process. So what if we use some natural phenomena that everybody can observe? So examples might be sunspots or solar activity on the surface of the sun, things like the weather, what temperature it's going to be tomorrow, how strong the wind will be, whether or not it will rain, or even cosmic background radiation, which is just noise that you can listen to from any point on Earth, and everybody should be able to read the same values. So these are phenomena that happen at such a large scale that it's fairly easy to convince yourself that nobody is going to be rigging the process. It's somewhat far-fetched to imagine that somebody would fly a spacecraft to the surface of the sun to modify what was going on in order to rig some lottery back on Earth. So that's great that it's publicly observable, and that in most cases we can accept the randomness here too. We have pretty good beliefs that enough days in advance it's impossible to predict low-level weather phenomena. The problem with these approaches is that they're fairly slow. For example, if your random signal is what the daily high temperature is going to be, you only get to read that once a day. The surface of the sun doesn't change too often. And you essentially reinsert the trusted party problem because you need somebody to observe the event. So let's say that we tried to use as a random signal what the temperature will be tomorrow in Princeton, New Jersey. We might get into a problem if I have my own thermometer that says that it was 73 degrees and somebody else has a thermometer that says that it was 72 degrees, and the difference between those two meant that a different person won the lottery or some other important outcome of the randomness. To get around that problem, we would probably need to designate and say we're going to use one specific person's thermometer to actually measure this phenomenon, or maybe we'll use the National Weather Service. But at that point, you've basically reinserted one trusted party who has control of the process. So a similar idea is to take financial data, specifically stock market prices, and say, can we build a randomness beacon out of that? And again, these are publicly observable, And there's a fairly good argument based on a bunch of complicated financial models that says that it's very hard to predict the low-level fluctuations of stock prices. If you could predict within a penny what the final price of a specific stock will be on the New York Stock Exchange tomorrow, you could make a lot of profit as a day trader from that knowledge. So the randomness is good, and it should be fairly costly to manipulate. You could try to rig this by, say, buying or selling stock to try to drive the stock price to a specific value that you want, but that has a real cost that you can compute. But the problem, again, this is fairly slow, because you can probably only read it once a day if you're reading one company's stock price. And again, it has this problem that there's a trusted party, namely the stock exchange, who has some control over the process. So even though the party running the stock market has a fairly strong incentive to establish that it's honest and that it's acting in good faith and reporting stock prices as they actually are based on market activity, there is the risk that they might try to change the price by a penny or so if it let them rig a valuable lottery. So the theme here with almost all of these approaches is that no matter what you do, it seems like you reinsert this one trusted party who has some control of the process. Of course, a big theme of these lectures so far is that Bitcoin has been an amazing technology at removing central trust from protocols that we didn't think that was possible to do before. So can Bitcoin pull the same trick off for a randomness beacon? Can we extract random data from the Bitcoin blockchain with the same decentralized properties that make Bitcoin so attractive? If we recall the fact that miners have to find a random nonce for each block, we think we might be in business here. Why can't we use the random nonces that miners are finding in the process of mining as a randomness beacon? So there's a fairly strong argument that you can't predict with high probability what the next nonce will be. If you could, you'd have a mining shortcut. So if you had the capability to predict what the next nonce will be with a probability greater than 1 over d, where d is the difficulty of finding a block, then you would have a faster way to mine than just trying nonces at random. And remember that d is pretty high right now. It's greater than 2 to the 66. So that means that every block that's mined in Bitcoin should have 66 bits of randomness that are impossible for anybody to predict. At least if Bitcoin is secure, there should be no way for any of the miners or anybody else to predict what those random bits will be. So once we realize that, it's fairly simple to turn the blockchain with minimal modifications into a randomness beacon. We simply take every block in the chain, take the entire value of the block header, and run it through an extractor function. And an extractor function, without going into all the details here, is sort of like a hash function and is designed to squeeze all of the random data out into one uniformly random string. And that will give us a nice randomness beacon, and every time a block is published in Bitcoin, we have new output from the beacon. So how costly would it be to manipulate this? So any miner has the capability, if they find a block, to discard it, to not relay it to the network, not publish it, not let it be the next block in the sequence. And they could do this if they find a block and realize that it produces a beacon output that they don't want. And it might not be the miner that decides this, it might be somebody who's trying to force the beacon to have a certain output, who says that they're willing to bribe miners. And if they find a block that's undesirable, this attacker will bribe and pay them more than the block reward in exchange for not publishing this. So let's say that you're trying to force some beacon output with probability p. This is just going to be a Bernoulli trial. So you have to discard some number of blocks until you happen to hit success. And the expected number of blocks that you'll have to discard is 1 over p minus 1. And recall that discarding a block is pretty expensive. You are going to lose the entire block reward, which is currently 25 Bitcoin, or around $15,000 US at today's prices. So what's the practical cost of manipulation? So say that you're doing a single coin flip. Like I said, the expected number of blocks that you are going to lose the reward for is 1 over p minus 1. And with a single coin flip, p is just a half. So you'll get that you have to discard about 1 block on average and eat that whole 25 Bitcoin cost. And if you have an n-party lottery where it's fair between all n parties, it's going to be 25 times n minus 1 Bitcoins. So this process will be secure as long as the amount that you're betting is less than that cost of manipulation. So essentially, if two people want to have an even odds bet, and they want to use Bitcoin as the source of randomness, this is going to be secure as long as they've wagered less than 25 Bitcoins, or again, about $15,000. So the advantages of this, it's somewhat remarkable that this is the first proposal that's really out there for a fully decentralized beacon. So a beacon that has no central point of trust. And compared to some other processes, it's actually fairly fast. It's not going to output as often as, say, the NIST beacon, which is designed to output as often as possible, but about every 10 minutes you'll get new output from the beacon. And it's also nice that we can precisely analyze what the manipulation costs are here. So we have a fairly simple model, and we can price the cost of manipulating the random output and how many block rewards you'll have to sacrifice. So the downside of using Bitcoin as a beacon compared to some of the alternatives is that the timing is a little bit imprecise. So suppose we want to read the value of the beacon tomorrow at noon. We don't know exactly which block is going to be published tomorrow at noon, because blocks are just published whenever they're found, not at any specific schedule. So we'd have to guess, based on the distribution and the average times, what block index will be published around noon tomorrow, but that will give us quite a bit of variance. And we'll also have to delay when we accept the result of the beacon based on the risk of a fork. So just like with anything else in Bitcoin, we'll probably want to have that roughly 6-block confirmation time before we accept that this really is the final beacon output. And the cost of manipulating this beacon may be too low for some applications that we care about. So if we're actually running the NBA draft and there are millions of dollars at stake, it may suddenly look worthwhile for one of the teams to start paying Bitcoin miners to manipulate this process. So it's an open question if we can extend the security of this construction to make it secure in a case like that, even when we have millions of dollars on the line. So one more really cool idea for what we could do with a beacon built off of Bitcoin. What if we extended the Bitcoin scripting language so that there was a special opcode to call the beacon? So currently there's no way to have any randomness in a Bitcoin script. And that's by design, because the miners have to be able to verify this, and they want to all be able to verify it and get the same thing. But if we use the beacon, the public source of verifiable randomness, then you could use the beacon to insert randomness into scripts in such a way that any miner could run, and they would run the script in the same way. So what could we do with that? Well, if we had one opcode that would make a random decision based on, say, the beacon output of the block before, we could replace that entire complicated lottery protocol with one script that just read the beacon once, and based on the results of the beacon, assigned the output to one of 3 keys, or n keys, however many players we are, and you'd be done. It wouldn't be a multi-round protocol, we wouldn't need bonds, we wouldn't need timed hash commitments, we could just use the beacon. So this is a somewhat out there idea, but there are a lot of cool applications for what we could do with this.